So, the objective to consider general functions and define general derivatives and examine their properties. Okay, so that's all useful stuff, but in a very vague sort of sense. It's like, well, I could define the whole course that way. So that doesn't really much, but it's true, but it's true. So anyway, the Jacobian matrix is the matrix of all first order partials of a vector valued function. Right? So that's something to keep in mind. Right? So you can have multiple first order partials of a vector valued function, and its value, no pun intended, I guess, comes in play mostly when you're dealing with 3 dimensions and beyond. Right? Because when we get into partials, yeah, it's nice to know that you could find partial derivatives in 2 dimensions, but it's not really necessary to think of it that way. You made it through 2 entire courses before you even thought about partial derivatives, and there's a reason for that, right? So here, what we're looking at is the 3rd dimension and beyond. What this is a collection of all the different partials, first order partials that could exist with respect to the different variables, right? And the blurb there just kind of gets across the idea that it gives you the set or a sense of the rate of change around a particular point in space along the surface, right? So when you're talking about the Jacobian, it's really just giving you the sum total, if you will, of all the different interactions of the rates of change in terms of the different dimensions that you have. So with respect to X, with respect to Y, with respect to Z and beyond, how those interact to make a rate of change, an overall rate of change at that location. Right. So in terms of an analogy, like when you're, we've done this, the going up a hill, you're walking up a hill. It's like, all right, you know what the rate of change is in the direction you're going, right? So like if you're going uphill, you know that there's a rate of change that's positive. It may not feel positive in your heart, but it's positive because you're going uphill. It's a positive slope. All right. Behind you would be negative, a negative rate of change. You'd be going downhill. Right. But in an oblique sense, as you're going left, right, or at some weird angle, like what's the rate of change in that regard? And what impact does it have on the movement? That's a different conversation, different question. So I kind of equated to how your ankle feels. You know how like you feel your thighs, your quads as you're hiking up that hill, you're huffing and puffing. You know how your lungs feel. It's tough, but how do your ankles feel? And it's like, well, what do you mean by that? Well, if you're walking along a smooth, flat surface, even if it's on an incline, your ankles aren't really taking the brunt of anything. Same thing with your knees. Right? Maybe the knees is not a good example because depending, like sometimes if you have an arthritic knee, you feel everything. So it's maybe not the best example. But if you're walking up a hill and it's not only on an incline in front of you, but on an incline to your right, you're walking along something that's got a pitch to it. You feel that in your ankles. Okay? So the Jacobian is going to take into account all of those other rates of change besides the obvious ones, and it collects it all together in one concise way, and it gives you a measure of the overall rate of change at that location. Right. So computationally, it takes a little work, but once you have it, you now have a measure that represents the rate of change for, it could be at a point or it could be at a collection of points, it could be at any point. If you look at the example, the first example that follows that, I actually solved this one out because honestly, it's just a pain to write it all. But what you're looking at is the Jacobian for the transformation equations to get from spherical coordinates to rectangular coordinates. Right. So what I did was I took the first order partials of each one, first with respect to rho, then with respect to theta, and then with respect to phi. Right. And so things kind of work out when you do it that way. Right. But it's a question of what do they work out to? Like, what did you get as a result? Well, right now you got an expression that represents the rate of change. We'll get into what the determinant of that actually means in a couple of minutes. All right, but for now, just finding the Jacobian is a matter of finding the first order partial with respect to first rho, then phi, then theta for each equation. All right, so you're treating in the x equals rho sine phi cosine theta, you're treating the rho as constant. I'm sorry, you're treating rho as the variable. Everything else is being treated as a constant multiple. So the derivative of rho is 1, so you'd be left with cosine of phi sine of theta. And same idea for the other entries down the first column. Right, but it's just the same as it would be as if you were taking the derivative with u, v, and w instead of rho phi and rho theta and phi, or rho phi and theta. Doesn't any order is fine, right? So on the next page, we get into Jacobian matrices associated with rectangular coordinates, right? And so I did another one. I did a couple, just so you had it on paper, because again, they get kind of messy, but it's still doable. Right. Now, in some cases, you run into a little bit of a trippy situation where it's like, all right, well, if I needed to find the determinant of this, how would I go about it? It's a 4 by 3 matrix. If I wanted it to be a 4 by 4 matrix, I could find the determinant. For these kind of problems, it's just the practice of getting it into the Jacobian form. All right. So, yeah, what's up, Sydney?
Sorry, I was just going to ask if the Jacobian matrix is going to provide like an explanation for why like dv is equal to rho squared times sine phi times d rho d phi d theta. Like when we're doing the triple integral.
It can, and there is a proof that involves this approach. And actually, I could go over that. Yeah, because I belatedly realized that I owe you all a proof on that one. I could show it that way. Yeah, it will actually go. It'll justify that. So yeah, you know what? I'll do that. I don't want to relegate it to a video. You know what I'll do? I'll do that first thing next class. I'll take you through that explanation. It's actually really cool. So yeah, it does actually explain the bounds for the triple integral. So good question and good reminder. Thank you. So I'll make sure I'll lead off class with that one. Let me make a note to myself before I forget. Send an email. The only way I ever remember to do anything. So explanation for bounds of triple integral order of integration. Spherical. All right. Yeah, definitely. I'll make it a point to go over that first thing. All right. So yeah, so I figured I'd take you through an example or two. There's one that involves an ellipsoid here. It's kind of an interesting twist. And then we can start getting into that connection that I've been promising between the matrix, change of variables, and volumes and so on, right? So I want to find, and we're using the notation here of y sub 1s and x sub 1s and all that stuff. So when I go to find the Jacobian here, I'm looking for the first order partial. I see three unique variables, x sub 1, x sub 2, x sub 3. Right? So this is a 4-dimensional equation because the x, if I replace x sub 1, x sub 2, x sub 3 with what we were used to calling them x, y, and z, then the dependent variable would be some new variable that we probably call w. That's what most people call it. And that would put us into the 4th dimension, right? So it's something that, we're beyond the ability to visualize it, at least in our heads. So we need some other technique that'll help us figure out the rates of change and all that good stuff. So that's one of the significant values of the Jacobian. So the first equation, I'm looking for the first order partial of y1 with respect to x sub 1, then x sub 2, then x sub 3. All right. So the notation is going to be a little crazy. I mean, you can skip the step where you actually write out your plan of attack, I guess. I'm just gonna, it's just good note taking, or at least in my mind it is. So I'm still gonna put it down. I don't want to skip too many steps. Is really what I'm getting at here. Right. So although I am going to copy and paste like my life depends on it. I just got to change my subscripts for the y's to 2s and then 3s. All right, so, okay, that looks terrible. Oh, terrible. Oh, for the love of Christmas. All right, I'm going to live with that one. I'm just going to move it over and I'm going to just tack on. Okay. I'm just going to hand draw it. That's what I'm going to do. All right, so I need the first order partial of the first equation with respect to x sub 1. Fortunately, there is no x sub 1 in there, which is great news because everything else is treated as constant, which means going to 0. All right, so 0. First order partial of the first equation with respect to x sub 2. That's just going to be a 5. I'm going to give it a fair amount of space because some of these aren't going to be quite so clean. And then with respect to x sub 3, there is no x sub 3 in there, so that's also going to be a 0. All right. For my second equation, I'm taking the first order partial with respect to x sub 1, which makes the sign part of it irrelevant. So just straight up power rule there, that's going to be 8x sub 1 to the first power, just 8x sub 1. With respect to x sub 2 and x sub 3, the 4x sub 1 squares are going to be irrelevant. So I'm going to disregard those, but I'm going to take the derivative. We're going to do a little chain rule here. Taking the derivative of sine gives us a cosine. So I'm looking at -2 cosine of the stuff on the inside multiplied by the derivative of the stuff on the inside. So let me get the -2 cosine of the stuff on the inside multiplied by the stuff on the inside. Now this is with respect to x sub 2. With respect to x sub 2, treats x sub 3 as constant. Derivative of x sub 2 with respect to x sub 2 would be 1. So it's going to be multiplied by x sub 3. And the reverse would be true for the next computation. But that's what I was saying before about spacing. You know, you kind of fall in love with a certain way of spacing things out and you realize you didn't give yourself enough room. So I'm gonna move some stuff over. So then for the last one in this row, it's same initial part, -2 cosine of the stuff on the inside, taking the derivative with respect to x of 3, hang on to the x of 2 as constant multiple. Derivative of x of 3 with respect to x of 3 goes to 1, so this should be an x of 2. All right. So then the last function, with respect to x of 1, there is no x of 1, so that goes to 0. With respect to x of 2, that becomes x of 3. With respect to x of 3, that becomes x of 2. All right. So this is my Jacobian matrix. I don't even know why I keep trying to do that with the auto draw tool. I'm gonna do it by hand. But now what I need to do is find the determinant of this, because they said find the Jacobian determinant. All right. Other question said the Jacobian matrix, or the last one was just flat out a statement. All right. Now I need the Jacobian determinant. All right. Which is one of the reasons why we reviewed, or in some cases learned, how to find a determinant, because we get the moments like this. And in years past, I foolishly made the assumption. Well, actually, there was one year where I just thought that linear algebra was a prerequisite for this course. So that was on me. But then I assumed that people had some experience with matrices, and I found out that the far majority of students had no experience with matrices. And so that's why, if it seemed like I was kind of go on off on the longest linear algebra tangent ever, it was for a purpose, and this is the purpose. All right, so I want the determinant of this. And we look at all the skills that we covered and all the different ways that you can find a determinant. And we want to be finding the most efficient way. I'm not seeing a triangular matrix, but what I am seeing is a matrix that has zeros for the most part, except for one entry across the first row. All right, so that's telling me that I should use cofactor expansion across the first row. All right, so I'd be looking at -1 to the, that's row 1, column 1. So to the 1 + 1 power multiplied by the entry 0, multiplied by the 2 by 2 matrix, which we can disregard as irrelevant, right? Plus -1 to the row 1, column 2, multiplied by 5, multiplied by the matrix that exists or remains when the row and column that contains the 5 are removed. All right, so that's telling me, well, fortunately there's a 0 there, but that's telling me that we're looking at, and this gets a little cramped, but 8x of 1, and then all of this business here. I have to resize again. So let me snag this. And then 0 and an x of 2. All right. Now, if I go across, continue going across the top row, that's great. We're going to get another 0. The only reason I showed the first row, first column was to get a sense of the alternating nature of the -1 and the +1. So now I'm kind of done with that. So I could just say +0 because I know that last one's going to zero out because the entry itself is equal to 0. Right? So this zeroes out. This becomes a -5, right, to the odd power. So -1 times 5 is -5. Diagonal down, 8x(1) times x(2). Diagonal up is 0. So we're looking at -40 x(1) x(2). All right. And so what this gives us is a numerical value that represents the rate of change if we know what x(1) and x(2) are, right? It's also pretty useful in the sense that it's telling us that the rate of change for any point along this surface in 4 dimensions. So we can't witness this. We can't draw a graph and take a look, but any point along that surface will have a rate of change defined by the x and y values or by the xy plane, right? So the position within the xy plane will dictate whether or not it's an increasing or decreasing or constant relationship, right? So that's pretty cool to be able to kind of determine without actually witnessing. There's some things that you got to take on faith only because you've explored thoroughly the dimensions that you can experience physically in the hopes that that would lead you to understanding of the ones that you can't experience physically. All right. So then number 4, find a rule that gives the volume of an ellipsoid. All right. So the ellipsoid, with the tech assignment, I'm just looking at the clock here. Got enough time for this. I'm just verifying. The ellipsoid, because next class we're doing surface area and vector field, and also what we're talking about with the that proof I want to show you. So the volume of an ellipsoid, I mean, you can look it up online. It's interesting, but it's something that we can determine because of the 3-dimensional figure. It's circular in nature. We have rectangular, cylindrical, and spherical coordinates. The coordinate system that seems most appropriate to this relationship would be the spherical coordinate system. But what we'd want to do is figure out some sort of rule that would allow us to determine the volume of any ellipsoid, right? But in order to do that, it kind of makes sense to make a coordinate system change, right? Instead of working in the rectangular coordinate system, we can redefine a new coordinate system to simplify this significantly, right? So if I look at this and I say, okay, I got x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. I'm looking at this and I'm saying, okay, well, that's not too far of a cry from the equation of a sphere, which is x squared plus y squared is equal, I almost made a circle, plus z squared is equal to 1. All right, so that would be the unit sphere, which is the simplest type of sphere, and it's also the basis of the spherical coordinate system. So if I could somehow turn the x squared over a squared equation into something along those lines, then that would make life easier. All right, so what I can do is I could rewrite this as x over a squared plus y over b squared. Nothing fancy there. That's just basic algebra that you may or may not have thought to do. That's the thing. It's like, doesn't make anybody feel any better when somebody says, oh, it's just basic algebra, if it's not something, it's not a step that you would have thought to do. But now you'll think to do it, right? And the reason why we make this move is because if I can define new variables to take the place of the x over a, the y over b, and the z over c, then I'll be in pretty good shape. Right? So, you can use whatever you want. We'll just use U, V, and W because it's, we're in the beginning of the alphabet. We'll go to the end of the alphabet. The variables to define variables. You think of like U substitution. What comes after, T, U, V, W. So it kind of makes sense. So U, I'll let equal X over A. V, I'll let be equal to Y over B. And W, I'll let be equal to Z over C. All right. So then what I can do now is I can redefine my X, my Y, and my Z value. All right. So I can let X be equal to AU. My Y would be equal to BV, and my Z would be equal to CW. All right, so we now have a relation that would allow us to redefine our sphere, our ellipsoid to be a spheroid, but we're changing the coordinate system. So instead of being in the XY coordinate system, XYZ coordinate system, we're redefining it to be in the UVW coordinate system and redefining X, Y, and Z to be proportional with those U, V, and W values, right? And that's also that we can say U squared plus V squared plus W squared is equal to 1, which is our definition of a sphere, but just in our new coordinate system, the UVW coordinate system instead of the XYZ coordinate system, right? So normally what we would say is that we would have some sort of, if we're thinking rectangular coordinates, which is what the original coordinates were given as, we would have f of x, y, z. Now, being equal to some vector containing an x, a y, and a z value, right? So what we want to do is shift that so that it's instead, we would say f of UVW, knowing that U, V, and W are defined as whatever we define it as, X over A and Y over B and whatever, right? So we could do it that way, right? So we could also say, because X, Y, and Z are defined as AU, I'll write it in vector notation, B, B, C, W, that our new function now has independent variables of U, V, and W, right? So that is basically, I'm sorry, this is a transformation. So there should be parentheses. All right, so this would be a transformation. So we would now have a vector that would be AU, BV, CW, where the independent variables again are U, V, and W, and A, B, and C are the scalars of those values. Right? So that transformation allows us to make it a whole lot cleaner. So then what I can do now is find the Jacobian of this function for any value along its surface. All right, so I'd be looking for the first order partial. I'm going to write it again. I know it's a time sucker, but it's necessary, I believe, anyway. So we're looking at, yeah, a brain cramp here. So partial with respect to u, partial with respect to v, partial with respect to w. But we're going to be doing that for each one of these equations. All right. So it's just kind of hard to visualize that there are actually multiple equations here. We're looking at these as 3 separate equations. We thought of as AU, comma, 0, 0. BV, oops, sorry, 0, comma, BV, comma, 0. So I'm decomposing the vector valued function into different components and looking at them each individually. All right. And so what we're actually going to do, as weird as it might seem, is we're going to compute the same sequence of first order partials, but 3 times, 1 for each of the equations. All right. And the reason why we're able to do that, and it's kind of a weird thing to be able to do, or seemingly anyway. The reason why we're able to do it is because an ellipsoid, just like an ellipse, is defined based off of its axes. And so if we talk about movement along, in an ellipse, it's major and minor axis. But in an ellipsoid, you have that third axis associated with the z. Right? So what we're looking at here is really just focusing on the impact of those axes on the ellipsoid itself. Right? So if I can get this dang thing to look good here. Minor miracle. I'm going to give up in a second. Right. And so this Jacobian is going to be pretty easy to compute, because if I take the first order partial with respect to u of my first equation is the word of the day, then we got a lot of zeros, so they're going to zero out. With respect to u, it's going to become an a. With respect to v, sorry, it's just going to become a b. All the zeros are going to remain 0. And with respect to w, the CW becomes crappy network. I don't know. Network being the second word of the day. So equation and network. All right. So that would give us the Jacobian, which in turn, if we're looking for the Jacobian determinant, is going to be pretty simple to compute. And I'll just do it up here. Because we learned that one technique for figuring out a Jacobian, a determinant, is if it's a triangular matrix, then you can multiply down the main diagonal, right? And so a triangular matrix tells us that you have zeros on either side, one or the other, in this case, both, of the main diagonal, right? So you can use cofactor if you want, but it actually ends up being unnecessary, because if you just multiply down the main diagonal here, right down that line, you get A times B times C. And that ends up being the Jacobian determinant. Now, it's not the volume of the ellipsoid, but it's a step in the right direction, right? So that's part of the fun, but it's not all the fun, right? So what this actually gives us is a measure of the rate of change of a surface on an infinitesimal level, right? So if we expand outward from there, or downward, or in whatever direction, depending on what set of dimensions you're working in, then you can collectively determine the volume over whatever interval it is that you're looking for. It's easier to visualize in obviously 3 dimensions. If you have a surface floating in 3-dimensional space and you know the rate of change in all the omnidirectional rate of change at a particular point in space, then you know the infinitesimal little bits of change going off in every possible direction, then what you're creating is an infinitesimal area. That's what the ABC is giving us. It's giving us an infinitesimal area. If we bound that over an interval, then we'll have what we need, right? Because creating the bounding would expand that infinitesimal area to cover, in a Riemannian sort of way, it'd cover all the space from the lowest possible bound in any direction to the highest possible bound in that corresponding direction, right? So what we would do here is use this as a multiplier of the rho squared, because it is spherical. It kind of makes sense to go in that regard, because A, B, and C really just kind of boils down to a constant multiple. If you know the values of A, B, and C, in the case of an ellipsoid or an ellipse, they represent the change from center. They're going to end up being constant values, or at least unknown constants. You would multiply that by the multiplier for integration for a triple integral, rho squared sine phi, d rho d phi d theta. I need more room. Okay. And then what we would do is integrate that over the appropriate intervals. Now, if you're talking about row bounds, we would go back to this relationship, because we're working with a transformed equation. That's the one thing that we don't want to lose sight of. That transformed equation is u squared plus v squared plus w squared is equal to 1. That led us to all of this stuff here. So we're not working with this anymore. We're working with this. And so we would think about how that's bounded. Well, it's a sphere. So what are the bounds for a sphere? Well, it exists between 0 and 1. I'm just going to resize a little bit again. You know, not the drill. In terms of phi, it's going to go, you know, as far as phi can go, which is from 0 to pi. It can go further, but then it would be doubling back upon itself, and then out to 2 pi in terms of theta, one turn around the unit circle. Right. So then it's the matter of integrating. So I would take this, integrate with respect to, well, just like that. With respect to phi, I'm sorry, rho, it's getting late. 1/3 rho cubed. I got my A, B, and C there. I can pull that out of the whole thing if I want, but I'm just going to leave it for now. Sine phi over the interval of 0 to 1. So that's going to be 1/3 ABC sine of phi. We're going to integrate that with respect to phi. Right. With respect to phi, we're looking at negative 1/3 ABC cosine of phi over the interval of 0 to pi. So negative 1/3 ABC cosine of pi is -1 minus negative 1/3 ABC cosine of 0 is equal to a +1. So we're talking 1/3 ABC plus another 1/3 ABC. And then from 0 to 2 pi, no, so that, I'm sorry, that's going to be 2/3 ABC. You knew that, but I figured I would say it. And then from 0 to 2 pi, we're integrating with respect to theta. And so we're just going to slap on a theta here. So 2/3 ABC theta over the interval of 0 to 2 pi. Let's clean that up. So we're looking at, is that 4 pi over 3? ABC as a general rule. All right, so then it's just a matter of multiplying it by the A, B, and C values, and then we'll have our answer. All right, so the A, B, and C values, just kind of jot it over here. A is equal to 1, B is equal to 2, C is equal to 3. Those would get chucked in there. Do a little shrinky dink. So we would be looking at 4 pi over 3 times 1 times 2 times 3. And so that would give us, well, I don't have to do the strike through, it looks ugly, but it's going to give us an 8 pi. And so that would give us the volume of the ellipsoid. Okay. And so, you know, in terms of taking the long way around, absolutely, but it does tie things in together kind of nicely, I think. The one weird part of it would be the concept of being able to split the vector valued function into the 3 separate equations. But that, like I said before, that's only, we don't typically do that. We can only do that because the ellipse is really defined based off of its axis value. So what we're doing is we're looking at, okay, the AU, the BV, and the CW as vectors that come together or compose them with one another to give us just the axes of the ellipsoid. And so by looking at them independently, it sort of makes sense because we're getting movement along the x-axis, the y-axis, and the z-axis, and therefore that, you know, the transformation into the UVW coordinates tells us that we're moving along the u-axis, the v-axis, and the w-axis. All right. So I don't want to keep you late, but I'm going to stop it there. Stop the recording. Stop the share.